How much do you know about how Kafka works under the hood? I mean, you can go a long way just knowing how it works logically, but it's like anything. If you want to get the best out of it, it does pay to peek inside and learn something about how it does what it does. Well, for this week's episode of Streaming Audio, we've brought in a real expert, Jun Rao. He's been working on Kafka since the very beginning. He's one of the co-founders of Confluent, and if you want to peer under the hood of Kafka, well, this week we're getting a guided tour by the guy who helped design the car. He's joining us fresh from recording an in-depth series of tutorials about Kafka's internals, so it's front of his mind. And if you find this podcast whets your appetite for gory details, well, you can learn even more from Jun over at our educational site. That's developer.confluent.io. The course is up now, it's completely free, and it's split up into logical modules so you can find the parts that are most interesting to you. Although, having said that, I've been going through the whole thing and I've learned something from every module, so if you've got the time, it's really worth it. But for now, let's listen to the man himself as he shines a light on some of Kafka's internals. My guest today is Jun Rao, who is one of the original creators of Kafka, original committers, the co-founder of Confluent, our company, and still an active developer on Kafka itself. I mean, I was stalking you on GitHub yesterday, and you reviewed 2 pull requests. So that's I know right. You're currently active. So welcome back to the show, Jun.
Yeah, thanks, Chris, and good to see you again.
Yeah, likewise. So to frame this, you have recently launched on our developer education site a course all about Kafka internals, how it actually works under the hood. And I've watched most of it, and it's like super rich meal full of information. So I thought, whilst we can't hope to do the whole course in this podcast, maybe I can pull some juicy nuggets out of your brain in the next hour.
Yeah, sounds good.
So let's start with this. So let's gradually work our way into the depths of Kafka. What is a Kafka broker? And by that I mean, what's it responsible for and what's it not responsible for? What's its boundary?
Yeah. Okay. Yeah. First of all, I think about that course, it's just, I think over the years, where we started with like an architecture of Kafka, right? But over the years, we actually have been improving architecture in various ways. We actually improved a lot of details to make Kafka more performing, more real time. So there's actually a lot of work went into Kafka's internals. So I thought, it's probably a good idea, just to summarize what we have done, right? So that most people would understand a bit how all the things work. In particular, for the broker side, I think when we started with Kafka, we deliberately had this design of separating the compute from the storage. Because it's like a lot of other systems, like a database, right? I think where you have some place you need to store the data, but you also need to do some processing for the data that you are storing. In the case of Kafka, right? We store data in real time as a continuous stream. It's like a log, right? That's essentially the storage part. Yeah. The second part is how do you leverage that storage, right? What do you do with that stream of data coming in? Well, that's the real-time processing part. So typically you want to, there's a lot of like ETR style processing, right? That's moving towards real time. You want to do this continuously. This can be as simple as doing some filtering projection, but can be more complicated stuff like joining 2 streams together, compute some window-based aggregation, right? And so on and so forth. So when we designed Kafka, we said, okay, so the broker layer is really in some sense the storage layer. We want that to be the place where we store the data. And then we want that to be good at delivering the data. Based on what the user needs. But it doesn't do too much of the processing. So all the processing of the data is done essentially on the client side. So that's the computation layer we have. So this can be as simple as just a simple application based on our consumer API, but it can also be a more sophisticated application based on Kafka Stream, where you do some of those more complex computational processing that I mentioned earlier, or can be like a KSQL DB layer, right? So all the more advanced processing will be done in that layer. What broker is doing is really two things. One is to be able to store the data, incoming data, as a stream in real time, as reliable as possible. And then when the user needs to make a subscription of the data, it can deliver the changes, right, to the user in an efficient and real-time way.
Yeah. Okay. So we've got this ladder of abstraction climbing up for processing, but that's completely separate from the broker.
Yeah, I think the idea for that is by having this separation, you can scale them out separately, because Kafka designed as a distributed system. Both the broker and the clients can run right in a distributed way, so that you can scale out the resources as you need. So by decoupling the broker from the processing layer, now you can scale them independently. If you have some storage need, right, you can scale out the broker, and if you want to scale out processing, then you can just scale out the application layer. So this also actually provides a little bit better like isolation, because in some of the cases, right, when you do the processing, you may want to run a little bit like a ad hoc logic that's specific to the user's logic, right? By running this outside broker, just protects the different parts better, because if you have some issues with your application level code, it's only impacting your particular application, but not really impacting the broker. What runs on a broker is really some predefined, like limited capability to retrieve that data.
Right. Yeah. And this is so let's dive a bit into the broker side of the responsibility. And you said it's worrying about real time and durable and scalable. So what are the principal techniques you employ for those three guarantees or aims?
Yeah. So let's talk about, I think one is the first thing we really wanted, right, to have in Kafka is to really solve that high throughput issue, because a lot of the traditional messaging system is really designed as a single node system. It wasn't like designed to handle those high volume of event stream, right? That's common in some of the modern architectures.
And you're there in the early days of LinkedIn, like facing exactly that problem, right?
That's right, because I think there, you have to dealing with not only just a traditional transactional type of data that's stored in the database, because dealing with like orders of magnitude more volume of data that are sort of non-transactional in nature. These are like click streams. These are like application metrics, various logs, right? IoT information. So these like as useful information as transactional information, right? For all the data analytics you want to do, but volume-wise, it's just far bigger. So the way this is achieved in Kafka, is just, I think fundamentally, this is actually designed from ground up as a distributed system. So by running multiple of those brokers, right, typically in a cluster, you can distribute the load among those brokers, right? Then you sort of need to have like unit to distribute your entities or resources, and that's the concept of topic and partitions. So that's sort of first thing, by having this thing together, you sort of have the architecture that you can scale out as you need on the broker side. That is, I think, probably the most fundamental reason, one of the fundamental reasons for achieving this high throughput.
Yeah. Is that why from the early days you had this key value basic unit where we're going to shard based on key?
Yeah, that's part of the reason. I think one is if you have keys, right, then you can do a little bit like a partitioning based on semantic. And this actually is useful for a few cases. It can be used for co-locating records, right, with the same key together. This actually can be useful for some of the processing if you want to do things like aggregating a bunch of values against a particular key, right? Having all the records with the same key being landed in the same partition and consumed by a single consumer is definitely convenient for doing this kind of computation. It's also used for ordering guarantees, which is also important because some of the a lot of applications, they don't necessarily want like a global ordering, but they do want some ordering within like a subdomain. Often is like per key. Think of like a key like maybe a per customer, right? Or maybe it can be a particular user or particular session. So having the ability to be guaranteed that everything happens within that key ordered strictly is useful for building some of those applications as well.
Yeah, that makes sense. So you've got like my click stream and my instant messages stream keyed by my LinkedIn username so that all that data is going to be ordered for me and on the same node for me.
Yeah, exactly. Because, for example, let's say if we understand how what's a like a user's watching behavior of let's say Comcast, right? Where having a particular Comcast users watching session coming in order, right, makes your understanding of that behavior probably easier because this is actually a particular ordering the user have been seeing the content.
Yeah, makes it far more processable. But then, so I see that you've immediately got a problem because once you've split something out, you've got to coordinate. Once you've sharded your database into lots of different machines, you then have a coordination partitioning problem, which I think you go into in the internals course, solving that quite cleverly.
Yeah, I think that's one of the things. I think for when the producer first send the data, right? So you sort of need to know, okay, which partition it goes to, and then this can be done based on key if the key is provided, right? Which will guarantee some of the semantics that I mentioned earlier, either is co-locating or ordering. Mm-hmm. If you don't care, we have the freedom just to spread data like more evenly. So that's on the way on the path when the data is coming in. Now, on the way out, right? So when you consume the data into the consumer applications, the same thing is happening. I think one thing with the concept partitioning is it actually allows a lot of parallelism, independent of the number of brokers on the consumer application side, because the degree of parallelism you have is really the number of partitions that you are consuming, which can be far more than the number of brokers on the server side. So what we see is in a lot of applications, when they process those messages, right, or records, their bottleneck is typically not on the server, it's really on the application, just because for each of the record they are consuming, sometimes they have to do some expensive logic. Some reason could be they just have a legacy system that they have to interact with, right? That has high latency. So the easiest way to get around of that, just to maybe to have more degree of parallelism, right? So you can hide that latency.
Yeah.
So for things like that, the consumer application often requires a lot of flexibility in terms like having more degree of parallelism, and then having partition is like a great way for achieving this parallelism for those consumer applications.
So you've got this deep relationship between the number of partitions and the way consumers handle load balancing.
That's right. Mm-hmm.
Yeah. Okay.
Yeah.
Maybe we should go a bit into that protocol because it gets us into the world of how you deal with recovery and downtime, right? This protocol of load balancing a consumer group?
Yeah. Well, yeah, in terms like recovery and load balance, I think the first thing, is I think on the broker side, a big part of the requirement is to have this high availability guarantee, right? Because Kafka is designed as a real-time system, right? People want that to be available all the time. And then the fact that it's designed as a distributed system just means, I think, there are a lot of servers you have to deal with, and at any particular point of time, there could be a broker that's down, right? Maybe you are taking it down for maintenance. Maybe there's some hardware issue, right? Even in those cases, we need ability to continue to provide this high availability of our service. So a big part of how we achieve that is the redundancy capability we added on the broker side. So on the broker side, we have the ability for you to have each of those topic partitions replicated. If you enable that, which I think pretty much everybody enables that now, you will have the same record be redundantly stored on multiple of those brokers. So then if one of those brokers goes down, you can be assured that the service will still be available on another copy of the same data. So that's one of the things to make our service truly highly available on the server side. Of course, if there's a real failure of a particular broker, we also have this recovery logic to make sure once the failed broker comes back, it can be completely in sync with the rest of brokers again.
Yeah.
Then it comes with the same high availability guarantee, I think, with the consumer applications. So the same thing happens with the consumer application, because typically when you run the consumer application, as I mentioned earlier, you typically will run multiple instances of that for better parallelism. And then we have this nice protocol, so which is actually around when it was first invented, right? It was really like a revolutionary thing compared with the state of ours around that time, which is we can magically distribute a load, right, of all the topic partitions this particular application is interested in subscribing evenly among those instances. And if one of those instances goes down, we can actually magically just reshuffle the load among the surviving instances. And the same thing, if you have a new instance added, again, we're just magically redistribute data among those instances. Everything happens like dynamically, automatically for the user. So the user actually doesn't have to do anything when they change the number of instances. This is actually a pretty big deal for our users, and it's a pretty convenient but effective way of consuming those data in a distributed way.
Yeah. But even that, right? So you say that was revolutionary at the time, but I know you go into your course that rebalancing protocol itself has evolved quite a lot in the last decade.
Yeah. So I think initially we designed this like a protocol so that all those independent instances in the consumer application can coordinate among themselves, right? Now, how do they coordinate? Well, to make some decisions, you think you need like a coordinator, right, to coordinate this distributed effort. So that's the consumer group coordinator capability we added on the broker side. And its responsibility is to understand, okay, how many instances are there in that particular consumer group, right? And then what are the things they are interested in? Then the coordinator is responsible for coordinate the dividing of the load among those instances. Mm-hmm. And then after that, is also responsible for keeping track if those consumer instances are still alive, right? Or if any of the new instances have been joining. So that's a lot of logic that's been added into the coordinator logic, which is pretty useful. I think over time, what we found is there are just a couple of things, I think, for some of the more advanced use cases where the initial design was a little bit lacking. So the first thing is every time when you have to do another rebalance, this could be either because an existing instance is dead, or maybe a new instance is added. You sort of have to shuffle the work, right, a little bit among those instances.
Yeah.
As part of that, I think the naive way, which the old protocol was doing, is to stop everybody, right, what they are doing now, right, and then clear their state. Because for some of the applications, you actually need, as part of processing, you need to maintain a little bit of state associated with the data that you are processing. So if you are owning a particular partition, sometimes you may need to maintain the corresponding state for that partition. So then the eBay would just say, oh, okay, since we know we have to redistribute work, right? We don't know what that work would be. We'll just clear up everything up front.
Stop
then
the world, pretend you never did it, and start again. Yeah.
That's right. And then you let the rebalance complete, and then you get this new distribution of work, right? Then you start building that state again. So then the first problem, of course, is, sometimes in some of the cases, you get back essentially the same work as you had before, or at least maybe some of the partial works that you had before, right? So in those cases, having to clear that state and then rebuild that state after rebalance can be expensive, especially if that state is large.
Mm.
The second issue is just, that's what we call this stop the world rebalance, because you are first stopping the world for everyone, right? When there's like rebalance is happening. Even though in some of the cases, when the new assignment you got, you realize you actually will be continuing with the same work or the partition that you've been doing the work before. So that's a second part that's a little bit inconvenient.
Yeah.
So the evolution of the group protocol we have been doing try to address both issues. We try to be a little bit smart in terms, what work we truly need to stop, right, and then rebuild state, so we can improve a little bit like both front. So we try to avoid unnecessary cleanup and a rebuild of the state associated with those partitions, but we also try to continue the processing for some of the data that in the end, may not need to be redistributed.
Okay, so you've gone from the original setup, which is a node going down, a new one being added doesn't need to stop the system, to a node going down, a new node being added doesn't need to stop some of the other people who are processing right now.
Yeah, we try to make that a little bit more incremental, right? So that's sort of the improvement we have been making. Another thing is just, I think a lot of the common reasons why you need to do the rebalance is really you are deploying new software, right? So you need to restart each of the application instances. Because you want to upgrade to a new version, you want to make some config changes, right? So in those cases, each of the instances will go down, but it actually will go back very quickly. Sometimes it's just like a few seconds, right? You bring it down and bring it up. So in those cases, we also added another option for doing optimization, where if you can tolerate a little bit latency, right, you can just say, okay, I know I'm bringing down an application, but I know it's going to be brought up pretty soon again. So in those cases, maybe it's cheaper just not to do those rebalance again, because in the end, it's the same set of instances will come back. So just wait a little bit, right? If all those instances will come back within a reasonable short period of time, then you can just continue with the assignment you had before. So in those cases, you can actually completely avoid rebalance as well.
Yeah. So this, and you go into that in your course. I know it's one of these tunable parameters that you can say, this is the amount of time you shouldn't worry us being down. We're coming back up soon.
That's right. To
Yeah. Yeah.
achieve that, I think, one is you have to set like a static member ID so we can determine know which instance you are, right? No matter how many times you are restarted. The second thing, you just you can tune that session timeout just so that if you can come back right within that period of time, you are still considered alive.
Yeah. Yeah. So that moves me on to another section, which is spiritually very similar, if I can say that. It's that has really evolved in unplanned downtime, which is our move away from Zookeeper.
Yeah. So that's another big sort of evolution we've been doing. So when we started with Kafka, right, I think we deliberately created this separation between our control plane and the data plane. So the data plane is what we called, what we discussed earlier about most of the things the broker has been doing. It's responsible for storing the data, right, for delivering the data, for making sure the data is like redundant. But there's also some metadata that we need to manage at a whole cluster level. These are the things like what are the topics, right, and partitions out there? Where are they located on the broker, right? Who is the current leader? Which replicas are like fully caught up in sync? This kind of stuff. So we need a place to store that information. So that's essentially is part of the control plane. Initially, that control plane, just for convenience, it's done on Zookeeper because it's a replicated consensus service. It's perfect for storing this metadata, right? Because we don't have to build something ourselves. And then it sort of served our need when we started. It actually allowed us to build a distributed system much quicker than before.
I remember the state of play back around that time, and Zookeeper was just your go-to distributed consensus tool, right?
Exactly. Yeah. So it definitely served its need around that time. But what we realized over time, which essentially led to this effort of replacing Zookeeper with a built-in K-wrap, I think are a few things. So one is we realized that for a lot of the user, I think managing like one type of distributed system is actually much easier than two types. I think for a lot of places, people are like okay with running a distributed system because now it's sort of the norm now, right? But if you can say there's only one type of the binary, right? You just deploy this type of binary to however number of instances you want, and then just start it up, right? That's actually a much easier thing to manage and understand. If you have to say, okay, two different type of binaries, right, and then they need to have its own sort of a membership and distribution, then there's like more work in terms of both deployment and of course the operational part, because you have to set up the monitoring system, right, for each, and then they probably are a little bit different, and then you have to of course collect the logging and other things, right?
Yeah Managing a group of nodes is hard enough, but they're managing stuff within those nodes, not being able to treat them as just units.
That's right. So that's the first thing. We said, okay, just I think if we have something that built in, right, we can eliminate the dependency of a separate distributed system. The second thing is really a lot on the scalability and performance thing. So in the data plane, because it's like distributed, right, we actually have achieved a lot of scalability for better throughput and performance. But for the control plane, it's really sort of single noded. It's really handled by a single node. And then Zookeeper, if you look at it, is a regular replicated service, not like a scaled out service. So as the usage of Kafka grows, right, what we realize is I think a lot of places people want to have more of those topic partitions. One is, just over time, more and more business data are integrated and consolidated in Kafka. The second thing is because partition is like easiest way to achieve parallelism. Often people just want to have more partitions over time, right, to achieve the scalability.
Yeah.
We always have a little bit this pressure over time. People just want to use more of those metadata. And what we realize, just part of it is because Zookeeper is like an external system, and then it's like a separate API. It's kind of hard for us to achieve this sort of scalability in terms of the amount of metadata that we can manage. So by switching to KRaft, which essentially is like a built-in implementation of a consensus service based on Kafka's internal log, we actually can achieve a factor of 10 in terms of scalability, in terms of how many of those topic partitions we can handle in the single Kafka cluster. So this will be a lot hard to do if we try to stay in the Zookeeper land. So that's a second sort of key benefit we get from this exercise.
Yeah, and I remember first learning that and thinking, okay, this is a good thing. The first time they're looking to scale out a data storage problem, they actually used Kafka to solve it. It's very much a dog food thing.
Yeah,
right?
That's another thing, just because we build that specifically for Kafka, right? We can leverage some of the capability and functionality within Kafka. We can also optimize it a lot more because it's like customly designed for Kafka.
Yeah, which inside out.
Right. And then as a side effect that, I think by having this metadata service like built in, right, in the KRaft layer, we actually automatically get a hot standby. So earlier, a big part of the problem is because all the metadata is stored in Zookeeper, right? We only have like a single controller at any given point of time, which caches this metadata stored on Zookeeper.
Yeah.
But the issue is if that controller goes down, right, the new controller doesn't have actually any data. So it really has to bootstrap the state by reading all those metadata at the cluster level from Zookeeper. And that, it really depends on how many topic partitions you have out there. So sometimes, you have a large cluster, this can take minutes just to reload that. With KRaft, the benefit is now all those metadata, right, are replicated and then cached in memory in the KRaft replicas. So one of those KRaft replicas, which happens to be the leader of the Raft quorum, would be the active controller. But if that controller goes down, now we can switch to any of the replicas of that KRaft quorum, which has a hot in-memory copy of all the metadata already. So it can take over as new controller much faster than before because it has the state ready to go. So in that case, I think that's another big advantage, for a large cluster with lots of those metadata. I think our controller failover story is much better than before.
And it ends up making
which indirectly allow us to have more of those topic partitions in the same cluster.
Yeah. And that presumably speeds up the process a lot.
Yeah, I think it just means, because of that, now your system is much more highly available because you can always act on things that needs controller. This could include like a leader election, right? Earlier, I think if you had hard failure on a broker, which happens to run the controller, you can't elect the new leader for those data partitions until the new controller has bootstrapped its state, which can be minutes, right?
Yeah.
But now if the same thing happens, Well, I think the new controller can take over and then elect new leader almost instantaneously. So in terms of like availability, it's much better than before.
Yeah, yeah. And we had Liz Fong Jones on the show a while back at Honeycomb, and she's doing like 2 million messages a second. And at that scale, downtime of a few seconds is colossal, right?
Yeah, exactly.
Yeah. So these are problems I'm assuming you didn't actually have to face on day one.
Once you have this system, right, I think over time, I think different users applications are always like, especially for some of the leaders in some of the tech industries, they are always pushing the envelope, right? So, which is good for us. We want to make sure we keep evolve this platform so that we can continue the innovation to serve like stronger or better needs for the users.
Yeah. Success comes with its own problems.
Yeah.
Yeah. I was just so I'll tell you something that slightly surprised me about the whole K-Raft project was I didn't realize, I assumed the metadata that you get for each node was just one big blob. It's just like, this is the layout of the cluster. But it's actually sharded too, right? It's partitioned.
Yeah. So the data is definitely partitioned because we have different topics. We have partitions, right? These are like distributed to all those brokers. But for the metadata, it's actually backed by a single log. You can think of as a single topic and partition. So all the metadata for the whole cluster.
Okay.
Today is like stored in a single topic partition. I think I love that, just for convenience, because think of Zookeeper, that's essentially it's like a single log, right? A single topic partition. So so we sort of carry that over, but we just make that single topic partition much more efficient than an external system like Zookeeper.
Okay.
In the future, I think it is possible to consider, to even shard the metadata if we have even more like metadata. So that's also a possibility. But right now, I think we're just starting with the first version of K-Raft. So for simplicity, we just want that to be a single partition.
Okay. In that case, I've misunderstood something. Perhaps you can clear it up for me, which is if you've got a single log for the metadata and it's just like one blob that keeps changing every time the metadata state changes, where does snapshotting come into that? Because I know you snapshot periodically for the metadata, but why is it not just the latest record?
Yeah, that's the thing. I think if you look at what's stored in this metadata log, right? These are a bunch of the changes to those resources related to the metadata. Think of if you change the leader for partition, right? We need to record that change, right? But a lot of other aspects that don't necessarily change. The assignment may not change, right? Maybe only the leader is changing. So for things like that, it's for a bunch of like resources, like whether it's topic, partition, maybe some of the configurations, we want that to be updated over time, either based on the request from the user or based on decisions that controller has made based on observing the healthiness, right, of the whole cluster. So all those changes are stored in the log. Now the issue is if you don't do something on the log, this log will just keep growing, right? Because you can't easily trim the data because you don't know which record in the log still carries the latest information for a particular resource, right? Because it is true we only care about the latest value for a particular resource, but they don't get updated at the same time, right? Some of the resources haven't changed the value for a long time. So you can't just easily say, okay, we'll just truncate the data for data that's older than 7 days, because that data may still include the latest information for some of the resources. So that's where snapshot is useful. So what snapshot is doing is essentially is to periodically to take a prefix of the log and then collect the recent value for each of those resources, which is designated by a key. We want to keep track the latest value for each of the key, right? That's because that's the only thing that we care about. So that's essentially the snapshot we'll be generating. Once we have generated that snapshot, essentially we don't need a prefix of the log anymore, because everything useful in that log is fully captured in that snapshot. So that's essentially the way how we can control the size of this log. We can bound its size as long as we periodically generate those snapshots.
Okay. So that's the thing I've misunderstood. I thought you had the metadata for the cluster, and every time it changed, you saved the whole thing to your topic, your internal topic. But actually, you're doing event sourcing on that metadata. You record, we updated this thing, and you've got this log of changes to the metadata, which you can then snapshot to get a complete picture periodically.
That's right. So log is the one that keeps track of all the incremental changes. And then snapshot is sort of like an internal way to for us to essentially for two things. One is to bound the space of the log. We don't want that to keep growing for like forever. The second thing is to for the process to rebuild the metadata state in a more efficient way. Because if the log grows like too long, right, you can still rebuild your metadata state from the log, but it can take a long time, right? Because maybe there are just a lot of things have been updated that you have to play through. But with this periodic snapshot, it allows you to rebuild that state a lot faster, because the snapshot essentially is like a cleaned portion of the log, right, which is much more efficient for loading.
Yeah, that makes sense. I kind of feel like we could go on forever, because the course you've produced is like full. You could almost do a whole podcast on every single episode, but let's not get too deep into the weeds.
Yeah.
Let me try and pull it back out a bit and say, you've got modules that do like geo-replication and focus on the producer protocol and the consumer protocol and load balancing and all these things. Without saying you should just watch them in order, what do you think is the most important or your favorite one of those modules in the course?
Well, yeah, it's kind of hard to say, because I think a lot of those capabilities sort of are added, right, over time to solve like a particular need. And then I think a lot of those are like a pretty interesting need for building various type of applications. But I think if you're relatively new to Kafka, right, I think probably you want to start with the fundamentals, understand a little bit just the basic thing, how Kafka stores the data, right, in a distributed way, how the data path, the data plane works, right, with the publisher and then with the subscriber, and how that interacts a little bit with the control plane.
Right.
Another thing is, I think a lot of the applications, they really want this redundancy capabilities. They want the data to be, of course, replicated for both high availability as well as durability. And over time, they want that not only for a single data center, but potentially for multiple data centers, for all those different environments they want to have. This could be between on-prem environment and the cloud, right? Could also be in the cloud, but across multiple cloud. So that's sort of a sequence of the capability we covered in the internal class. We started with within a single Kafka cluster, how would you provide redundancy through the internal Kafka replication in the data plane. But we also have like a more advanced module for going beyond even a single data center. So we talk about if you have a multi-data center environment, how would you provide like a similar high availability and durability guarantee even across those environments. And there, I think there are quite a few like different options depending on how, for example, how close those data centers are, right? And then what do you want to do in this environment? Do you want to switch the applications, right, seamlessly from one cluster to another, or you want maybe lower latency? So we have like different options even for geo-replicating environment as well. So I think that probably for a lot of the places where they really want to put like mission critical applications on Kafka, this sequence of high availability and durability capabilities are probably relevant to them.
Yeah, that's one of the ones where you're probably going to know if you're growing into that space that that's something you must hit soon. Right?
That's right.
But you might, and I've watched all of them, I think, except geo-replication now, maybe one or two. I'm going to watch it anyway because it's just interesting how much detail you manage to get into in like a 10-minute video.
Yeah, I think it's it's an area where a lot of companies, when they grow over time, right, is an area where they often are looking into.
Yeah. I think on that, like I say, we could do an hour-long podcast on every one of your videos, but let's not do that. Jun, I'm going to let you go. I'm going to say thank you very much for letting us pick apart some of your brain. And if anyone wants to catch more, they can see the course on Confluent Developer. Thank you for your time, Jun.
Yeah, that's good. Yeah, thanks a lot, Chris.
Cheers. And that was Jun Rao. And I have to let you into a little secret. After we stopped recording, we got chatting about those kind of soft social issues when you're building a tech company. And, a sort of agile-ish view about how big traditional enterprise companies have a completely different feedback loop to modern cloud providers. And it changes the way they build things and what they decide they need to build. And I just wish we kept the tape recording because it would have been fascinating. But instead, I think we'll have to have Jun back on the show soon. Long before that happens, I hope you'll check out his tutorial videos, link in the show notes. They're quite short individually, but they are absolutely jam-packed with knowledge. So if you took one every lunchtime, in just 7 days, we could make you a manual. That course also has exercises led by our very own Danica Fine. And when you reach those, you'll want a Kafka cluster to play with. You can easily get one started at confluent.cloud. And if you sign up with the code podcast100, we'll give you $100 of extra free credit. Meanwhile, as ever, if you have thoughts, questions about today's episode, please get in touch. My contact details are always in the show notes, or you could just leave us a comment or a like, a thumbs up, a review, 5 stars. Let us know you enjoyed it. And with that, it remains for me to thank Jun Rao for joining us and you for listening. I've been your host, Chris Jenkins, and I'll catch you next time.